organizers of this event. One thing I want to mention in the very beginning, we will be recording this event because we want to share the recording online then, so that other people can also watch the video. If you don't want to be in the recording, please keep your camera turned off. You can still ask questions later on via the chat, for example. So if you write your question in the chat, we can read that out loud. Yeah, the plans for tonight, we have 2 talks planned, one by Dmitry, Dima, and one by Sophia. But before I go into the details here, is the result of the survey we just did. So it seems that we have almost a uniform distribution across the different experience levels, which is great also for the discussion later on. So thank you for participating here. See like 8 people, more than 5 years interested in NLP, 5 people less than 1 year. It's very nice mix, very nice to see that. Yeah, one other thing I wanted to mention, because we also have many new members in the group. You probably have seen the deepset logo in the upper right-hand corner, and you might be wondering what's this about. So deepset is the company that organizes this event. It's an open NLP meetup, open to everyone, but still we need some resources to organize that. And actually I'm myself working at deepset. So working in the intersection of NLP and open source software. And we are of course also hiring. So if you're interested or know somebody in NLP and open source, feel free to reach out. Especially we're looking for a team lead in open source engineering right now, but also for senior software engineers. But yeah, details if you want to ask me later. Now regarding the agenda for tonight, we have like 2 talks I mentioned. One is about the landscape of vector databases in NLP. And this talk is about like 20 minutes. And then we have 10 minutes for Q&A. After that, we have a second talk by Sophia about overcoming DPR's input length limitation with a model called PARM. And again, there are 20 minutes for the talk plus 10 minutes for the QA afterwards. And then finally, after that, we will have some virtual get-together in Zoom breakout rooms. So smaller groups to discuss a bit, to get to know each other a little bit. Yeah, so that's the plan. And I'm very excited that we got 2 speakers here that can really talk about very recent, very advanced topics. So Dima is principal data scientist at Silo AI, and he's also the host of the Vector podcast that you can find on YouTube. So maybe you check that out later. But for now, I would like to hand over to Dima. Dima, yeah, the stage is yours. Very much looking forward to your talk.
Well, thank you very much, Julian. Thanks for having me. Let me share my screen. All right, cool. So I hope you guys see my screen. I'm gonna have like a co-presenter, Max Irwin, who has been on the same team with me. Yeah, he's waving there. And we'll try to make it as quick as possible. Obviously, we have time constraints. So just really quickly about myself, I have a PhD in natural language processing. My topic was in machine translation. That was like 10 years ago. I have like 16 plus years of experience in search engines, in different setups, from startups to multinational giants. And yeah, I call myself an expert, but obviously there is a lot to learn in vector search engines. And as part of this journey, I started a Vector podcast to learn from the makers. I'm blogging also on Medium, every finding I make, and I'm also a committer on search quality assurance tool called Cupid, which was developed by Open Source Connections. And this tool is an amazing tool. If you didn't see it, please check it out. Yeah. Just to set the stage, part of this discussion will focus on the algorithm that we invented in the team called SISU. I'm from Finland, and so SISU means grit or perseverance. And this is exactly what we needed when we were part of this competition, because we are not an established company with this research unit. We just had curiosity and wanted to have some fun in the process. And you see the names here: Max, Alex Simonov, Arne Talman, Leo Joffe, Alex Klivitz, and myself, basically forming a team around spring last year to tackle the billion scale approximate nearest neighbor algorithm challenge. Just for the scope of this presentation, I will briefly introduce what is vector search in a nutshell. I will talk about main vector databases and also neural search frameworks that also make use of databases in some case. I will also provide you some practical materials that you can use if you would like to get into this topic. And also, if time permits, I will show you a couple of demos. So I want to start with this presentation by Martin Fowler that happened exactly 10 years ago, and he spoke about NoSQL databases. And I highly recommend you to find this presentation on YouTube. He's an amazing speaker, and he clustered or sort of categorized databases, NoSQL databases, in these 4 categories: document, graph, key value, and column family. And I claim that we witness the tectonic shift today when there is a 5th database type created, and that's vector database. Because it's not SQL, we can as well put it in the bucket of NoSQL. I quickly checked Google Trends, what's going on in the space of like vector search or neural search, as some people call it, versus inverted search. So inverted search is more traditional keyword search. And you can see that over time, the blue line, which is the neural search, begins to win and probably just speaks to the volume of documentation and blog posts and materials posted on this topic. And inverted search kind of is more or less stable, ups and downs, but looks like neural search is gaining its momentum. So I will start by kind of in this topic going a little bit deeper, like what is vector search, and probably it's familiar to many of you, but in a way it's a way to represent your objects, let's say documents, songs, images, anything that you have in a geometric space, usually of very high dimension, in the form of an embedding. And so a vector essentially will be something like an example here. You know, this is a floating point vector. It could be integer, it could be binary, whatever it is that you are using to represent your objects. And at small scale, let's say you have thousands, tens of thousands of objects. In principle, you could just use an exact k-nearest neighbor search to find all the neighbors to your query, right? But at larger scale, when you go to millions, tens of millions, billions, you cannot do that because exact KNN will be like a linear scan through your data set, and it's impossible to really like complete it within reasonable time. And so you have to do some trade-offs there. Usually you trade some precision for speed, and that's exactly where approximate nearest neighbor search algorithm space arises. And this is a kind of a quick screenshot from Deviate vector database, which shows you kind of geometrically, if we ran PCA on our multidimensional space, you know, we could represent it in this 3-dimensional space. And you can see here that semantically newspaper, magazine, and article cluster together. Apple and banana is fruit clustered together. And so that's why nearest neighbor search is powering semantic search today. So what are the use cases? Why people do this? Obviously, semantic search is number one. You also have image similarities. So you go away from text to something that is not text, like image or sound. You can also create multimodal experiences. So for example, you could search images with text, or maybe vice versa in some cases. You also have recommender systems that are powered today by similarity search. And also there is a very particular case in e-commerce, but it's very important for business. For example, zero hit long tail problem. So when people type something that your e-commerce system doesn't have, you might as well, instead of showing kind of predefined page, use similarity search to find similar items. This space is crowded. Big players are in the game. So Spotify, that you might be familiar with, has invented the algorithm called Annoy, just a funny name. Microsoft with Bing team has invented a few algorithms. One of them is Zoom, another one is DiskKNN, and they have also developed the product around it, Azure Cognitive Search. Amazon is investing into this as well. as part of OpenSearch. This is like a fork of Elasticsearch, and they have been using a well-known hierarchical navigable small world graph algorithm. Google is also in the game with their algorithm called SCAN. All of these are papers, and you could read them freely if you're interested. Yahoo as well invented an algorithm called NGT. Facebook implemented a very famous framework called FICE, and they've done a bunch of work in product quantization there. Then Baidu, Yandex, NVIDIA, Intel, and list goes on. Just to scare you, you don't have to remember this slide. This is how many papers have been published on this topic. A lot of algorithms, derivatives from each other, and so on. And there is always place to invent a new algorithm. And so I would like Max Irwin to go through the algorithm that we invented as part of Big NN Challenge.
Yeah, thanks, Dima. So what you're looking at here are the results. I get 3 slides, so I'm going to try to explain this all in 3 slides. It's quite hard because there's a lot of research and practice involved in getting to something like this point. But we talked about trade-offs before. Dima mentioned, you trade speed, and in this case for recall, where you can see the queries per second is the y-axis and the recall is the x-axis. So there's no such thing as perfect. You're never going to get, so up and to the right is better. You're never going to get to amazing speed with perfect recall. You always have to do some trade-offs here and there, depending on how you're configuring your algorithm and your platform that you're using. I wanted to show this because this has been the catalyst for a site called ANN Benchmarks, which has been around for a while, which is actually started by Eric Bernhardsen, who's the person who created the Annoy algorithm for Spotify, and a lot of other people. And that's been a benchmark system for a while that shows different algorithms and how they perform on a benchmark like this. And then in the past year, a group that was gathering for NeurIPS announced the big ANN competition, which is billion scale competition. So how many vectors can you index and search in very practical constraints? So there's memory constraints, there's CPU constraints, when you get latency and queries per second and recall. So those are the things they mentioned because these things are popular for big businesses who have billions of vectors they have to index and retrieve very, very quickly. So the blue line here is what we started with, and this is we didn't do great in all categories here. This is our best. We show the best, of course. There are others where we didn't do so good. This is actually 10 million vector set. Our billion vector set didn't do as well, but we showed an improvement of 12% recall for the fastest optimization, and it's quite good. And you can see as you go right on the x-axis, you can see it kind of gets to almost 0.8 over there. About 7.76. So you're never going to get to 1.0 when you're doing things like this. So how do we get here? We're the red line in this equation. So we made use of face with the baseline. We started with the configuration that was at the blue line. And I'm going to talk about product quantization very quickly. And product quantization, basically you take a vector and you split it up into subvectors, and then each of those subvectors you get a centroid. So you're not actually reducing dimensions in product quantization. You keep the same number of dimensions, but you're reducing the possible values that can occur in each dimension. So this is the theory behind product quantization. So when you index vectors in product quantization, you specify certain things like the number of centroids for each vector, how many subvectors you have. So the number of subvectors is m, the total dimensions of the vector is d, and then you specify k, which is the number of centroids you want to optimize for. So this is the foundation of what we started with, and our hypothesis of many. We had a lot of hypotheses. We were trying a lot of different things, of course, but we came up with this idea of, well, instead of just splitting the subvectors at some given point and just taking them as they are in order, is to reorder them and reorder them in such a way where splitting these subvectors up will give a more efficient representation of a centroid. So in order to do that, we explored Kolmogorov-Smirnov tests, which is looking at which looks at 2 dimensions, and it says, well, what's the distribution overlap between these 2 dimensions for all points in the space? We actually took a sample here. It might be cut off at the bottom, but it's 100,000 points we looked at the top out of 1 billion. So you do this, and you do this for every dimension. And you see, well, which dimensions have most overlap in terms of distribution, and you can see the red or the orange, the brightly colored things are less distributed, less overlap, and the dark is more. And you can clearly see patterns here. So our hypothesis was, let's analyze these values. Let's do this and just do a search for all, do all pairs and see what the KS test is. We also used variance inflation factor, which is another way of looking at which dimension you could drop and see if it reduced or increased the variance in the set. Well, we never increased, but reduced the variance in the set if you dropped it. And the ones that reduced it the less versus the ones that reduced it the more, in comparison with other dimensions, will give you some hints as to the data set. So we reorder these vectors by just pairing closely related dimensions together, just reordering them, and then passing them through the same index. So this is actually independent of any vector search platform you would use that uses product quantization. You could use it with Face. In theory, you could use it with maybe even Pinecone or something. Dima will talk about that a little bit more. But other engines that use product quantization, you could use this. The punchline for this, though, is that we found that there's actually an important lesson here, which is no matter which algorithm you're choosing, always look at the data, of course, and look at how the data represents to itself and into the algorithm that you're choosing. And there's always going to be a close relationship between certain types of data, certain types of vectors, and the engine and algorithm that you chose, and try to optimize for that as well. But there are a lot of data scientists in the room, so I'm sure you do that anyway. But it's just important to take another look at things before you just go picking something off the shelf without thinking about it.
All right, thank you, Max. This was a deep dive into the ANN algorithms, and now I will progress into the clients to these algorithms in a way. So the vector databases, and this is going to be based on my blog post that you can find on Medium. So there are 7 databases that basically call themselves vector databases, and I've calculated quickly that 71% of them is open source. There are still more commercial players in the mix, which is totally fine for business, and all of them are businesses. And I will start off by calling out Milbus here first. This is a open source system, self-hosted vector database. And here you can see on the right, the diagram, which shows kind of like their overall architecture, but this just to tell you that they care a lot about scalability of the entire search engine, starting from indexing your vectors, reindexing them, and also searching them. And one cool feature of this database that I found is that they have an ability to index data with multiple ANN algorithms. So you can pick, let's say, HNSW, you can pick also product quantization, and then just see what works for your data set better, because you know the ground truth. Yes, there is another database called Pinecone, and this is kind of, in some sense, opposite to Milbus in the sense that it's not open source. It's fully managed database. So if you don't have a headache of running your own vector database on premise, you can buy a service from Pinecone and essentially get a similar, experience where you will just have it as a service. Again, it's fully managed vector database. It has a single stage filtering capability. That's how they call it. So essentially, many ANN algorithms, they miss the filtering capability. So as you search for the nearest neighbor, can you also filter by some parameters? And this is typical for use cases in business. For instance, like if it's a fashion search engine, you might want to search for sweater, and you might want to filter by specific color, size, or price. The third database that I wanted to show you is called Vespa. This is probably the oldest on the market, and so it has a lot of features built in. It's open source, offered to you both as self-hosted and managed version. And its key sort of value prop is that it offers you more than the vector database. So it's actually like a platform where you can do computation over your large data set. And then again, you can embed your data, store in the index, and store it in such a way that you can like efficiently query, select, and process the data on top of that process. You can also customize it quite heavily, and also they pride themselves in saying that they are geared towards deep learning, and so they have Tensor as the first-class citizen object. The next database is called BB8, and it's also open source, and also managed and self-hosted options are available. What blown me in this database is that it has expressive query syntax. It has GraphQL-like interface, for those of you familiar with GraphQL. So it's very expressive. If you look on the diagram here, they have vector index, object storage, and inverted index all coexisting in the same deployment, in the same database. And that makes, that might solve a lot of problems down the road. For example, when you have data drift in large scale deployment. And one wow effect that I want to call out is that they have an impressive question answering component. And so I think that this might be kind of useful for some demos to impress your management. The next database is called BALD, and it was developed by Yahoo team in Japan. It's also self-hosted, doesn't offer the cloud, but it's kind of cloud native architecture. It's also fully open source. And the key value prop for me is that it uses the fastest ANN algorithm to date called NGT. You can actually check it out on ANN benchmarks. And it also offers you some customization points like re-ranking or filtering algorithm, which are implemented as plugins to this database. The next player is called GSI APU. APU is Associative Processing Unit, and this is the only vector search hardware backend. So if all previous ones were pure software with some low-level optimizations occasionally, but here we deal with a hardware vendor. So essentially it's like a APU board that you plug into your server, and it turns into a vector database. It operates on billion scale, and what's cool is that it extends your Elasticsearch or OpenSearch capability to similarity search. So you don't have to switch to another database if you're already using Elasticsearch or OpenSearch. And they offer on-premise and hosted APU kind of board backend. And it works through the plugin here. So basically, like all communication goes through your Elasticsearch, and then your queries and your data get forwarded to this APU backend. Cool. And I believe last but not least, there is a database called Quadrant. It's currently self-hosted vector database. They have cloud in the roadmap. It's fully open source. And they pride themselves in what they call metric deep learning. So Max alluded to this in his presentation, but essentially, like for every database, you will be faced with the question, which metric function to use, right? So how to actually express the similarity of your objects. And this will be dependent on your data set, and Quadrant offers tools, and I think they will evolve more. And that will support your sort of data science process in designing the vector search engine index. Cool. With vector databases covered, the next one is semantic frameworks, as I call it, or layers. And here the situation is different. 57% is open source. It's down from 71 in vector databases, and it's exactly same number of players to my knowledge. DeepSet offers Haystack, all of us know, focusing on NLP. And then we have a player called Gina AI, which doesn't constrain themselves only to NLP, but they offer like a set of tools, to deal with different parts of your sort of data science, like fine-tuning your model, for example. There is another startup called Feature Form. They focus more like on feature storages and embedding hubs, because the moment you want to productize your semantic search engine, you will also need to deal with various versioning problems and also how you store, what's your ground truth and so on. And there are a few more companies like Zero AI, Hebia, who focus more like on specific niches, or like Zero AI focuses on NLP and Hebia focuses on NLP for finance, but they actually deliver like a knowledge base to you based on your documents. And a couple more. So RAS AI, it's based on virtual assistants, and then Moves is a new player here, developing multilingual vector search. All right. So to summarize, there is like a basis for all of this happening today. Algorithms, HNSW, PQ, inverted index, LSH, Zoom, DSKNN, body PQ, and list goes on. And then there are users of these algorithms, and also they extend, these are the vector databases, and they extend the algorithms to be more performant, also support filtering. And on top of this, I would like to think, and I'm open to discussion here, is that we have neural frameworks like Haystack, Gina AI, and the list goes on, that actually can use vector databases as one of their building blocks. I think semantically on top of these sort of software components, we have encoders themselves. So we need to choose an encoder, or maybe we need to fine tune it to our data set. And then as we go closer to the user, we will have an application business logic where we need to decide, okay, how do we combine neural search with traditional keyword search, which symbolic filters to choose, and also how to implement our ranking. Then obviously we have a user interface and a happy user on top. So this is like a pyramid of success where I think this whole industry is moving slowly. I will also really quickly, I know I'm over time most likely, but I would like to also kind of offer you a path for how to choose a vector database framework, and should you go with open source or maybe a commercial sort of managed option. So you might start asking yourself a question: do you have your own engineering team in-house? And if you do, you might as well go for a framework vendor or maybe a self-hosted database. If you do not, then maybe you should choose like a higher level systems like Hebia AI. The next question you can ask yourself: do you have an embedding layer? Or is it okay if vector database will do like the embedding process for you? And so if you have your own embedding layer, then choose a just pure database which will store your vectors like Quadrant or Milvus. But if you're okay with database computing these vectors for you, then you might choose Viviate and Vespa. So they will have some off-the-shelf models or ability to integrate the model inside the database. Then you can also ask yourself, am I focusing on NLP only? Do I see in the future that I will focus on something else? If not, if you're only focusing on NLP, consider Haystack. But if you don't know, or maybe you have a larger focus, consider using Gina AI. If you want to quickly test before investing into this solution, then I would offer you to subscribe for free trial of Zero AI or Hebia, a similar tool, and don't kind of waste your time on infrastructure. But if you already are ready to invest your time, then obviously pick an open source solution. And last but not least, you need to ask yourself a question: do I want to bother hosting this database myself, or I'm okay with somebody else managing it for me? And so if you're okay with hosting, obviously you can choose like an open source database. But if you'd rather prefer somebody else to worry about it, then maybe it should be Pinecone or BB8 or GSI and so on. All right, I think this would be a quick segue to the demo, and I hope you guys see my screen. So this is Muse. Muse stands for multilingual vector search. And here, I just wanted to show you that with vector search, you can bring in a new experience where users can type their queries in a different language than your data set is. So the first query I will use is miten elää onnellinen elämä. So in Finnish, it means how to live a happy life. And so when I click this, I get books. Actually, this is like an Amazon data set. And so it returns me books in English. And if I click this query in Dutch, history of science, it will bring me books also in English because that's my data set, but kind of magically it has translated my query, right? But it doesn't do the translation, it uses the vector search behind the scenes. And
So,
last but not least, this one is in Chinese. Sorry, was there a question?
yeah, maybe Dima, we can use it as a bridge to the Q&A because we're running over time. Maybe
Awesome.
one of the users can ask a question because I understand, right? You could type in any product query here, right?
Yes.
Any other, maybe if there are other questions, but as we're running over time, let's open the stage also for questions.
Absolutely, sure.
So yeah, I have a basic question that how do we handle the duplicate vectors as indexes in the databases?
Was it duplicate or?
Yeah, duplicate. So I have like 100 duplicates, which are similar vectors of same length. And then I am kind of inserting in iterations like every week. So what happens to the indexes if we use any algorithm, let's say any ANN algorithm?
Yeah, I think if it's semi duplicates, then they will kind of be clustering together, right? So you will have like very like dense clusters in your space. But if they're complete duplicates, maybe I would try to kind of filter those out. Like I wouldn't try to index them. But to be honest, I don't know how database will respond to that. I think it's easy to test.
I might also add that approximate nearest neighbor and k nearest neighbor can be used as a form to find duplicates where you may not have known they exist, right? So you want to find things. So you can have a blog post, for example, that you maybe blog spam or something, and it's like the same content, but maybe the header is different. Maybe they threw some keywords in there, but it will be very, very close. And you can look at the distance between the two and try to understand. Maybe some features completely overlap and are identical. So that's something to make use of. As per how to remove them from databases, that's up to the different database implementations. Some of them don't support updates and deletes right now, so it's actually kind of hard, but others do. Some algorithms like HNSW, it's very difficult to delete. You have to go and sometimes you just rebuild the graph. But different engines have ways to do it because they've added their own functionality on top of the algorithms that were described in the academic papers.
Yeah, Lalit, you raised your hand. Yeah, please go ahead with your question.
Thanks, Julian. So, like in a vector search, I wanted to know which in this open source space or any like closed source also, which one is the good for the update use case. So as far as I know, like it is like very good. You insert new vectors, it is fine. But if there is a use case where you want to update the existing vectors, how good and which one is a good in this use case?
It's an excellent question, Lalit. Thank you. To my knowledge, every database does it, and so this is like pretty much a very important part of a final product because as part of your product development in this space, you will likely be fine-tuning your model, and when you fine-tune your model, the vectors might shift a little, right? And so now you need to go and remember, okay, which vector was it? How it was stored in the database, and then replace it. So essentially every database offers this capability.
Like mainly performance wise, like so let's say you're running the system live and on the production level system, and you constantly getting this update queries. So mainly in a live situation, in offline, you can just dump the old index and reuse new one, but in a live running system, this so yeah.
Yeah. Actually, pretty much all of these databases are production grade, and also some of them are used at very big scale, like billion vectors, right? And so they have this flow where they do need to update also live, right? So, but if you're interested how they do it, you can actually dive in a bit more into documentation of each of these vector databases. You know, they will have load balancers, they will have replicas of index, and so when they have updated, if you do heavy update, it will be done on some replica and then replacing your online replica, so things like that. But obviously, these databases are being designed for very high load.
So another user raised the hand, I think.
I have the follow-up question for the previous question. Can I complete that? Sorry.
Somebody else raised the hand earlier, I think. Shintan, maybe?
Yeah. Thanks, Julian. Greetings. I have a question that in the demo which you presented, whenever it's running really fast. So I have experienced that the time taken for computation of embeddings is generally at stake. So how do you guys manage, or in this particular demo, or any ideas? Indexing is done, everything is ready, but it's a bigger query is given in the search box to compute that embedding. How do we accelerate that? Thank you.
Yeah, that's also a great question. So we don't use any acceleration here. You know, these are fairly short queries. These are not like documents or paragraphs of texts. And so we just compute the embedding on the fly. But if you find this kind of difficult for your use case, maybe under load you experience a lot of latency, there are like solutions that try to speed up or scale out your embedding computation, particularly, and I didn't mention it, but in Milvus database, the team behind Milvus, they also implemented a new framework called TOI, and so that offers you like a full suite of kind of managing such situations. Of course, you also have commercial products. I think Hugging Face offers
Infinity.
Infinity. Yeah, exactly. Thank you. Yeah. So, and then NVIDIA also has a similar product like that. So basically, at that point, you might need to go kind of lower level, right, closer to your hardware. And so companies like NVIDIA, for example, could also innovate, and they do in this space. Hope that answers your question.
Okay, so my thing was that in this one of the databases which you presented, any of them have this built-in capability? No.
So actually, for example, I can call out Viviate and Vespa. So they have essentially the embedding layer inside the database. And so you can also compute it outside. But if you're okay with the database computing it, then they will also scale it for you, right? So if you give more horsepower, then that part will be scaled. And also, of course, if you are going one level up in this diagram that I was showing here, so if you use like a neural framework, then Gene AI and Haystack, I'm pretty sure, will offer you some capabilities to scale out the embedding process. Perfect.
Thank you.
I think we have like time for one more question before we jump to the next talk. So
can I, is it okay to ask a second question?
Yeah, please go ahead. I mean, you were fastest, and I think we also can have questions later on in the chat. So even if we started with the next talk, I hope that Dima and Max will be happy to answer questions via the chat as well. Yeah, I see the thumbs up.
So I have certain embeddings with a model which is based on word piece embeddings. And then I have the same set of examples I have embedded with the sentence piece and if I compare both shares a different, different size of vector. And then if I index them, is it a good idea? Let's say I have like past few months, I have worked on a word piece embedding, and then I stored all my vectors indices. And from now onwards, I want to use a sentence piece one. So is it a good idea to like mix both of them, or else do I have to like recompute everything with single you got my question, right?
Yeah. I hope I did. I mean, I don't think there is a universal answer to your question, but rather I can point you to like what vector databases can do. So for example, you don't have to constrain yourself to indexing only one embedding per your document, right? For example, in BB8 and others, you can actually index several fields as embeddings, right? So you can, like in your example, you said you might have portion of a sentence or maybe paragraph as different embeddings, right? But you might also embed some other fields in your document, like I don't know, size or title or color, whatever you have in your items, right? And then you can use these different embeddings during your search process, and you can actually assign different like weights in the ranking, right? So maybe you pay attention more to paragraphs in some cases, or you pay attention more to sentences. So that totally depends on your use case, and that depends on your kind of product vision as well. But there are tools to achieve different goals. I hope I answered your question. Sorry if I didn't understand it fully, but yeah, at least.
Yeah, I mean, thank you very much, Dima and Max, for this talk and also for answering many questions. As I said, hopefully you can answer some more of them in the chat. For now, let's jump to the next talk and let me introduce our next speaker.
Yeah, sure. Thank you.
Who is Sophia. Sophia is a PhD student at Technical University in Vienna. Feel free to share your screen already. And she will present some topic, a new paper that is actually published on arXiv yet, but not in the conference proceedings because it's accepted at the upcoming ECIR conference. That's the European Conference on Information Retrieval. So just remember that where you heard the news first about this paper, not at the conference, but at this Open NLP meetup. And with that, I hand it over to Sophia. Sophia, the stage is yours.
Thank you, Julian. I hope you can all see my screen. Thank you for the nice introduction. So my name is Sophia Althammer. I do my PhD currently at the Technical University of Vienna. And I'm really happy to present you our paper called Passage Aggregation Retrieval Model, short PARM, for dense document-to-document retrieval. So in this talk, I will first introduce what dense passage retrieval models are themselves. So dense passage retrieval models are basically like models for semantic search, where you have text which you embed. And then we will present our model which we proposed, the passage aggregation retrieval model, and go into the workflow, the experiments, and also the results of our paper. So first of all, let's go to dense passage retrieval models. And these models are proposed in the subfield of information retrieval. And here the problem is that given a query, we want to retrieve documents from usually very large corpus, which are then ideally relevant to the query. So here we only operate on the text of the document and also the text of the query. And then traditionally, this is solved with a general retrieval pipeline where, given the query, you have a first stage of retriever which retrieves, let's say, the top 1,000 documents from the whole corpus, which are relevant to the query. And then in a second stage, computationally more expensive stage, we can do a re-ranking so that the relevant items come on top of the list. And then the results can be given to the user as a re-ranked list of, let's say, top 10 documents. So, and traditionally, this was done with lexical matching using EO25. But now with the upcoming of neural models and also contextualized language models like BERT, we can use this semantic knowledge for the retrieval. So yeah, traditionally, the first stage is done with an inverted index, where you store all the words in your corpus. And then the first stage retrieval is done using only lexical exact matching. And now, instead of only using lexical exact matching in the first stage retrieval, it's proposed to use dense retrieval. So this means you embed the query and also the documents in your corpus into an embedding space. And with this embeddings, you can capture the semantic information of documents and also of the query. And therefore, you also overcome problems like lexical mismatch between the query and the documents. And for this, you use a neural encoder, which encodes all the documents in your corpus. And then at query time, you embed also the query in the semantic space, and you use a nearest neighbor vector index, as we've seen in the presentation beforehand, in order to find the nearest neighbors in the semantic embedding space, which should be ideally the relevant documents to this query. And this can then be used as part of a larger pipeline, where you then also apply a second stage re-ranker, which is computationally more expensive. And for doing this first stage dense retrieval, there is the BERT dot model. This uses a BERT language model for embedding the documents of the corpus and the query. And the embedding is then compressed to a single vector using CLS vector output of BERT. And then the BERT dot model is trained on aligning relevant documents and queries to each other, so that the nearest neighbors of a query embedding are the relevant passages to this query. And then the relevance is scored with dot product between the CLS embeddings of query and passage. You could also use different variants of the similarity scoring, but usually it's done with dot product. And this then allows easy and also quick, hopefully approximate nearest neighbor search. And here, the good thing is that you can pre-compute all the embeddings of the passages beforehand offline, and then at query time, you only need to embed the query with BERT, which is computationally expensive. And then you only have to score the relevance with the embeddings, which you already pre-computed. And this is why you can also actually use those in production systems. So, but then, and then you apply a nearest neighbor search. Once you have trained dense passage retrieval model, you encode all the passages in your collection. And there, during the search, you only encode the query on the fly. So, but those dense passage retrieval models have limitations. So far, they've only been shown that they work very well for web search, but for web search, we are in a very constrained setting. So first of all, the queries are often short passages, and also the passages in the corpus are websites, and they're usually short. This works because only BERT has limited input length. So this works well for passages, but if we have longer documents or longer queries, it does not work anymore. And also what's very important for those dense passage retrieval models is that you have large amounts of training data, because you need to train them a lot, so that they learn an embedding function which makes sense for storing the relevance. So these are advantages we have in web search. But if we now look at other domains where we would also like to apply dense retrieval, these limitations become challenges. So in our paper, we look at a document-to-document retrieval task in the legal domain, which is called prior case retrieval. So here the query is usually a long document, like a legal case. And also the documents in the corpus are usually very long documents. And those documents exceed the input length of BERT, and therefore we cannot directly apply dense passage retrieval models. Also, another limitation we have in this specific domain is that we only have a small amount of training data, which is then also a challenge how we can train the dense retrieval model. So I quickly want to show you an example of the task legal case retrieval. So this is a task where the query is actually a legal case, and you want to find other prior cases which are relevant to this case or for solving this case. And for this case, we already see that they have a structure, the query documents, they have an introduction, they have the summary, and they also then contain multiple numbered claims. So this is the problem setting we have. And for this, we propose our passage aggregation retrieval model, which then overcomes limited input length of dense passage retrieval models. And the passage aggregation retrieval model liberates the dense retrieval models from limited input length. We also investigate how we can train the dense retrieval model on only limited label data. And for this, for our experiments, we consider the document-to-document retrieval task of legal case retrieval. And to give you an intuition already, how PARM works is that we thought one query paragraph could only determine relevance to a whole document by only one paragraph of the document. So it is not necessary that every paragraph of the query is relevant to every paragraph of the document, but maybe only one paragraph is relevant to one of the documents. So therefore, we look at the relevance for the overall document on the paragraph level and handle those long documents by splitting them up into their paragraphs and looking at the relevance of the paragraphs between each other. So now we'll see the workflow of PARM. So as I said before, we look at the relevance on the paragraph level, and therefore we create a paragraph level index of documents where we split up the documents into the paragraphs. And then at query time, we do the same for the query. So we have the query document, we split it up in each query paragraph, which then does not exceed the input length third. And then we retrieve for every query paragraph relevant paragraphs from the paragraph index. And then we're not interested in the paragraphs, we're actually interested in the documents. So therefore we replace the paragraphs then with documents they come from. So then this gives us a ranked list of documents for each query paragraph. And therefore we need to aggregate those different ranked lists for each query paragraph to one overall ranked list for the whole query document. And we do this by proposing an aggregation function called vector-based reciprocal rank fusion. And this aggregation then takes into account how often a document appears in different lists, but also takes into account the semantic vector embedding of the paragraphs. So I will now go more deeply into the aggregation strategy we propose called vector-based reciprocal rank fusion. And here we combine the advantages from an occurrence-based aggregation called reciprocal rank fusion, which counts how often a document appears in different lists. For example, on the right side, you can see the document 1 appears in the first list and also in the second list. So therefore, the occurrence-based score would be higher. And then we combine it with the topical embeddings of the paragraphs of each document. And with this, we make a weighted sum of the paragraphs which get retrieved, weighted with the reciprocal rank fusion score. And this is then the overall representation of the document, which we use for relevance scoring with the query. And then we also investigate different training strategies. As I already said before, dense passage retrieval models usually need a lot of training data so that they show performance improvements compared to lexical retrieval with, let's say, Beam 25. And therefore, we investigate how we can train the dense passage retrieval model for our task. And here we investigate if we either use a data set with labels on the paragraph level, or then we also have an additional data set on the document level where we have more, like where we consider each paragraph of the query document as relevant to the paragraph of the candidate document, if the documents are relevant to each other, and if not, then we consider all paragraphs as not relevant to each other. So with this leads to, like, with the paragraph level data set, this leads us to very accurate labels, but there we have less labels. And with document level data set, this leads us to a lot, but potentially noisy labels for training the dense passage retrieval model. So here we also investigate how we can train the dense passage retrieval model the best way. And we see that combining the training with both data sources leads to the best results. And then I will also go into our experiments. So we conduct our experiments on 2 different data sets for legal case retrieval. One is from a workshop called Lead. They provide data sets for like legal case retrieval, where you have relevance annotations on document level and also the paragraph level. And then we also use for evaluation of our PARM model a test collection from case law, which consists of 100 documents which are annotated for testing how well the system works. So, and then first of all, we investigate in our first research question how the aggregation works for PARM. So our baseline is here the reciprocal rank fusion aggregation. Then we compare disaggregation strategies to the aggregation strategy we propose, vector-based reciprocal rank fusion. And we can see in the table that the vector-based reciprocal rank fusion outperforms the reciprocal rank fusion aggregation for the models based on dense passage retrieval. So here we use dense passage retrieval model trained on BERT, but also one trained on the basis of legal BERT. So this is a language model pre-trained on legal corpora. And here we see that the aggregation strategy we propose outperforms the reciprocal rank fusion, which only takes into account how often the document appears, but does not take into account the topical embeddings of the paragraphs. So here we can see an advantage and a gain for the retrieval effectiveness in terms of recall if we also take into account the topical embeddings of the paragraphs. And then in our second research question, we want to investigate how well does now the dense retrieval perform in comparison to traditional retrieval with BM25. So BM25 is just lexical matching, matching like words which appear. And so in the graph, you can see the recall at different cutoff levels. The yellow line is the dense retrieval with without our model PARM. So here the disadvantage is that we have to cut off the input length for the query and the document, and therefore the performance is very bad. The red line is the traditional method using lexical matching with BM25. So BM25 has no like input limitation and can take into account the whole document as a query and also as the documents in the corpus. And then the two blue lines refer to the retrieval with PARM, either during the retrieval with BM25, but still on the paragraph level and then aggregating the results, or then with a dense retrieval model, also on the paragraph level and aggregating those results with vector-based reciprocal rank fusion. And here we can see that PARM for dense retrieval outperforms the BM25 baseline and also outperforms the PARM with BM25 at higher cutoff values. So this then shows us that using a semantic search, we can find relevant items which cannot find by only lexical matching, because maybe there are synonyms, maybe there are like semantic concepts which are not captured in the lexical matching. And this is exploited then by dense retrieval. And then with PARM, we can also make dense retrieval feasible for long documents as a query and also in the corpus. So yeah, thank you all for your attention. And what I really want you to take home is that, first of all, that dense passage retrieval models improve the first stage retrieval compared to traditional lexical matching models. That the model PARM we propose is a model for document-to-document retrieval, and that PARM improves the first stage retrieval for lexical and also for dense retrieval models. Yeah, and I've also open sourced our paper on arXiv, and we've also open sourced our code and also the models. In case you want to use them, you can just find them on my GitHub.
Yeah, thank you, Sophia, for your presentation. Let's see, there are some questions. Nobody raised their hand yet, I think. Maybe you can say something about future work, right? This is a usual topic, I think, also for these research presentations. Do you have anything in mind where you would continue working on that topic, or somebody else could continue working on that?
Yeah, definitely. So we now investigated only the task of legal case retrieval in the legal domain. And a retrieval task, which is very similar, would be prior art retrieval in the patent domain. So there the task is given a patent, you want to retrieve patents from a corpus which are relevant to the query patent. And there we also have very long documents. We have a very technical language and also not so many training samples. So this is a question how then the model would generalize if you use it for another task in another domain.
Yeah, right. Yeah, patent domain, of course.
Yeah.
Sebastian Arnold raised his hand. Please go ahead.
Hi. So this is Sebastian from Coralie in Berlin. Thanks for the great talk. I think that's very interesting. I'm curious if you have also gotten more into not finding entire documents, because as you just mentioned, they are very long at some point. And I think people are especially interested in finding like the little nuggets in these long documents, maybe even books. And you mentioned that you are not interested in retrieving individual passages, but can you maybe elaborate a little bit on this?
Yeah, sure. Yeah. So overall for this task, we were not interested in retrieving only the paragraphs which are relevant to a query paragraph, but of course it gives some explainability to the model. If you can say to the user, okay, this document is relevant because of this paragraph, maybe. So this gives a chance to like explain why we retrieve the documents. And I think this could also be very, like in this case, for like legal case retrieval, it could be very relevant for the users themselves. Because often in like legal search engines, you also see like this claim relates to this claim, and then you see the cited claim, stuff like this. Yeah.
Okay, thanks.
All right. There are many people raising their hands. Maybe somebody who hasn't asked a question in the other talk first. So Ahmad, please go ahead with your question.
Yeah, hi. Thank you for your talk. I actually saw your paper in Twitter. I just skimmed over it, but I have a question about the last results that you showed.
Mm-hmm.
And the question is the DPR model fine-tuned for your task, or does your model performs also good as a zero-shot model? Because I mean, BM25 is basically a zero-shot model. You can use it anytime. And how does that compare in other domain?
Yeah. So yeah, you're right. Like BM25 is totally unsupervised. Here for for our experiments, we trained a dense passage retrieval model starting at bird checkpoint and then only training it on the relevance annotations from our task. We also experimented with using a, let's say, pre-trained dense passage retrieval model, which is pre-trained on web search, but this showed very poor results. And what else can I say about this? Yeah, so I think also that, there are some investigations about unsupervised like search, or also using maybe like doc2vec embeddings of vectors for like search relevance, but they are really unsuccessful. So you really see that those embeddings are first trained to like represent semantic linguistic information, but not to encode some notion of relevance in the embedding space. So this is why you need to train those embeddings, because originally they were just trained on like linguistically representations, but not on representations for like relevance between two items. So this is why you need to train the embedding model to align relevant passages to each other.
Okay, thank you.
Maybe then next Lalit and then Shintan again.
Hi, Sophia. Nice talk. Like my queries related to mainly how you, what is this? Have you tried the split strategy also? Like, if I understood correctly, the queries also splitted as similar as the passes. And so how have you tried multiple split strategy? And what if the single claim also bigger than the BERT limit, then how you handle this scenarios?
Yeah, so for this task, the splits were kind of natural because you already have this natural structure of the legal document into the introduction, the summary, the claims. We also did some investigations how much like percentage of the passages exceed the input length of BERT, but there were only like 80% or so exceeding the input length. And then we just cut them off, assuming they don't exceed so much. So for this task, we didn't investigate different splits because it was really working out very well with this. There are some investigations also from other works, splitting up documents into like, let's say 200 words, also with like sliding windows, so that you have some overlaps in the passages. And also we investigated how to like generalize this approach to patents. And there you also have a natural ordering of abstracts, of claims, of a technical description. And here we also were investigating different splits of text. But here so far the results are not really good. But I really agree that performance of PARMs depends on the splits and how well they're chosen, or how much they also make sense for the overall, like, let's say, topical structure of document.
Okay, then Chintan, please.
Yeah, thank you, Julian. Thanks, Sophia, much for the wonderful presentation. I'm stuck with this document-to-document similarity problem for like many years, and I just need your one input with your experience. What is the performance time? Let's say if I have 100,000 documents already indexed, or let's say 1,000, and if a new document or legal contract of pages, then 60 pages, something is injected into the system, how long does this entire pipeline take? I know it depends on hardware and the kind of models, but rough idea in terms of big notations.
Yeah, I think so. If you're really referring to like a 60-page long document, I think first of all, the indexing would take very long because you have a lot of paragraphs which you need to index. I mean, 60 pages would probably make up, I don't know, maybe 6,000 paragraphs or so, or maybe 600 paragraphs. So then the indexing would take very long, but I mean, this is just something you need to do beforehand, so this you can do offline. And the query time, so dense passage retrieval models outperform BM25 with, let's say, an implementation with files, for example, with approximate nearest neighbor search. Then the latency is quicker than, for example, BM25. Of course, you need to do the latency for, let's say, 600 paragraphs. So then probably it would be maybe like 5 times slower than BM25. Then the aggregation itself is very cheap. That's a very straightforward and quick approach. So this would not add a lot of computational time, I guess. Yeah, so I think that should be feasible. What's really takes a lot of time is then pre-indexing all the paragraphs in the corpus.
And embedding computation as well, right?
Yeah, exactly, yeah. I mean, there are also approaches where you use smaller embedding models, like the Stillbird, for example, and then you would also have a smaller embedding model. Yeah. But I think for more efficient approaches, I would more look into papers like Colbert, for example.
Papers like, please come again.
Colbert, for example, where they pre-compute embeddings for words, and then they just do like semantic matching with the embeddings of the words, for example. I think these would be like also very good models.
Thanks, Sophia. Much.
I just posted the link to the paper in the chat. I think we have time for one final brief question before we go into the breakout rooms. So sorry for letting you wait so long. Shari, could you please go ahead? Or you can also write in the chat and I can read out your question.
Hello, can you hear me?
Yeah, we can hear you. There's some background noise, but please go ahead with your question. Or you can also write it in the chat and I can read out. If not, then we can also have a question in the breakout rooms, I'd say. So then let's start with the breakout rooms. I'd say with the 60 participants we still have, maybe Anna, you could please, let's say, set up like 10 to 15 breakout rooms. So when we have like groups of 6 to 5 people in each room, I think like 10 breakout rooms should be fine. And then I'd say we do 2 rounds of breakout rooms, and then maybe let's say for like 10 minutes of breakout rooms. I think that's fine. We can also stop the recording then. Okay, so see you in a second in the breakout rooms.